Good afternoon. Thank you. Thanks for the organization for the opportunity to talk about my work. This is a joint work with Arturo Fernandes Perez from UFMG, and some of the main results were on my PhD thesis from 2017, and these have been published in the Journal of Geometric Analysis last year. This is my first time presenting in English, so my English is a little rusty and rough on the edges. We might end up with a good laugh. So, our main goal here is to study germs of singular real analytic Levi-flat hypersurfaces with two distinct purposes. Concerning normal forms for those, we aim to generalize some previous results. We study germs of the following form. This one. Assume that our hypersurface is given by the real part of a complex quasi-homogeneous polynomial plus higher order terms, which are real analytic in dimension 2. We aim to find a way, specific coordinates in which this hypersurface writes itself as the real part of a holomorphic function. The second part, I don't think I'll have the time to speak about it. It is concerning the same nature of the problem, but in which the change of coordinate preserves the volume form, preserves volume, isochore, change of coordinates. So this is the notation I'm going to use. It's pretty standard, I believe. And I'm gonna skip some slides here because it's the usual language. So, if you watched Rogério's talk in Monday, he talked about Levi-flat hypersurfaces. So this is our setup. Let M be a germ of real codimension 1 irreducible real analytic subvariety at the origin of Cn for n greater or equal to. We may assume that it is the zero set of a real analytic function. Its singular set is nothing more than this intersection, and the regular part is its complementary in M. The Levy distribution is nothing more than the kernel of this application here. And if this distribution on the regular part is integrable, we say that M is Levi-flat. It is locally, if it's integrable, then it's locally foliated by real analytic codimension 1 foliation, which we'll call L in M star, the regular part, the Levy foliation of M. It can be given by this real analytic 1 form here, which makes our life easier. And the integrability condition writes itself in this way or this way here for each p in the regular part of M. The function f that defines our Levi-flat may be we have its complexification, okay? It's nothing more than switching this variable here for another complex variable, which we call w here. Right? We work with its power series, assuming it converges in a small polar disk around the origin. And we also have the complexification of the Levy form, which is now holomorphic. And if the Levy form is integrable, then this one is also integrable. We have the complexification of the Levy of our hypersurface, which is now a complex variety in C2n. And the complexification of the Levy form may be divided in two separate parts. Both of them defines the same foliation, now a holomorphic foliation in MC. And we may work with both alpha and beta. They define the same foliation and the same singular set. Now, the dimension of the singular set of M, the algebraic dimension of sing M, the singular part of M, will be the complex dimension of the singular set of its complexification. And we have a lemma that establishes conditions for the leaves of the holomorphic foliation in M to be closed. This is from Arturo. And now we may start talking about their normal forms. This is from 1932. This result is from Cartan. Around each non-singular point of a Levy flat, real analytic Levy flat, there's a coordinate system in which the foliation is just the real part of the last coordinate. There are several versions of the same result here. This is called the local normal form around a non-singular point. And this completely describes the structure of a Levy flat with non-singularities. And the natural question is to study those Levy flats around singular points. In this case, isolated singular points. This has been studied by several authors: Bedford, Burns and Gong, Brunella, Leibl. In the case of the Levy form being non-integrable, there are previous results from Tanaka, Chern, and Moser. And in particular, both Burns and Gong and Cervolins Neto prove the following theorem. If you have a Levy flat given by the real part of the sum of squares here, plus higher order real analytic terms, then we might find a coordinate system or bilomorphism in which this M writes itself just as the real part of the sum of the squares. Very well. This means that these higher order real analytic terms may be discarded in adequate coordinates. Several other normal forms for quadratic Levy flat hypersurfaces are also described by Burns and Gong. Some of those Levy flat hypersurfaces may not be given as a vanishing of the real part of holomorphic or a meromorphic function. For those that can, we may indulge ourselves if we can describe for them normal forms in this sense here. Well, Fernandes Perez gave several normal forms for Levy flat hypersurfaces. In particular, if you take Levy flat hypersurfaces, real analytic Levy flat hypersurface given as the vanishing of the real part of the Arnold singularities of modular 0, I guess it is a well-known set of singularities, you may also describe normal forms for these Levy flat hypersurfaces. Well, with this in mind, we ask it as a problem. Can we find normal forms for Levy flat hypersurfaces, real analytic, in the real analytic case, given by the other kinds of singularities described by Arnold, the higher modular ones? Well, this is the starting problem of my PhD thesis, in which I started to study what was done previously in these cases. The hardest part is in dimension 2. That means all these terms does not exist, here, and here. And I noticed that those singularities are given by quasi-homogeneous polynomials. So I tried to be lazy and compute once for them all. Yeah. So what I ended up with my hands was this. Yes, in the case you take real analytic Levy flat hypersurface given by the vanishing of the real part of a quasi-homogeneous polynomial in two variables, plus higher order terms. The important part here is that Q has an isolated singularity at the origin. So there is in fact a germ of biolomorphism, a new set of coordinates in C2 that allows us to write M as the real part of Q plus a finite set of a linear combination actually of elements of the monomial basis of the local algebra of Q with degree higher than the quasi-homogeneous degree of Q. In fact, this completely generalizes all these of this list and several other cases, several other Arnold singularities, and in fact, the amount of terms that appear here is exactly the modular of the singularity that you input here. So those C are constants. And in the case of singular real analytic Levi-flat hypersurfaces, given in this form, vanishing of the real part, they are all described now, except on the most general case, take M given by the real part of any holomorphic function. This is still an open problem. So, how goes the proof of this result? If you assume that M is given by that form, yeah, Q is a quasi-homogeneous polynomial, then there is a very nice factorization given, it goes something like this. In 2 dimensions, it's like Q of X and Y given by a constant plus X to M, Y to N with the product of, this is a finite product. I'm going to use J. So it's X to B minus C, J, Y, Q. So Q is a quasi-homogeneous polynomial in 2 variables, and to have an isolated singularity, M and N both belongs to the set 0 and 1. It's not hard to show this result. We take the complexification and we show that the algebraic dimension of M is 0. Separate the Levy form in alpha and beta, which allows us to work with a very nice form for eta. And the hard part of the proof is actually computing the holonomy group of the foliation. So it goes something like this. We start with M here, and it's singular here at C2. When we complexify, we have a copy of this setup here. Here is MC. Here is 0 at C4. And we perform, there it's a blow up, but it's actually a weighted blow up. So it goes, we obtain a weighted projective space as the exceptional divisor here, and a copy of that everywhere else. And here is the pullback of this. Here is the complexification. So this obviously has singularities, and when we do this, we obtain intersection of the singularity with the exceptional divisor, and if you take a non-singular point here and a transversal section, we may actually take these loops here and compute the elements of the holonomy group. And we show that each of these elements, if we consider this as a set of diffeomorphism of C around the region, they form a finite linearizable group. That is, every element of this group has finite order. So, and the existence of the first integral follows from a lemma from Fernandez Perez, and then there is the extension of the Levy foliation to the ambient, which will be a holomorphic foliation from a lemma from Cerveau and Luiz Neto, 2011, and then it allows us to write M in this form. M is now the real part of a holomorphic function. No more real analytic high-order terms. Now, with an argument, I owe Rogério Moll for the invaluable help in this part. we might show that f holomorphic function is actually q plus higher order holomorphic terms. That defines what Arnold used to call a semi-quasi-homogeneous function. And now it follows from Tougeron a lemma from Tougeron that there exists a biholomorphism in which f may be written as q plus a finite sum of elements of a monomial basis with degree higher than the homogeneous degree of q. Therefore, we find that M is simply real parts of a holomorphic thing. Yeah, it's called the amount of terms that appear here, this n here, would be what is called the modality of the singularity q. Yeah. Of course, all of those have modality 0, so there are no new terms when you switch the coordinates. And for higher modality number, there is exactly that amount of terms in the normal form. Now, concerning volume-preserving normal forms, we have two similar results. Yeah, if you take the holomorphic volume form around the region, yeah, we say that it's isochore or volume preserving if it writes itself as this. In 1977, Weil posed the following question. If it is possible to find a volume preserving coordinate system around the origin of Cn, in which any germ of function f is right equivalent to its Hessian? The answer is no, but he has shown that you may find a power series of f in which the coordinate change is volume preserving. This is exactly this or minus this. So we have this result. If we assume that we may find a volume, if we assume that we have this real analytic Levi-flat hypersurface given by the zeros of this f, then there exists a volume preserved German of biholomorphism around the origin of Cn, and there is a power series of this, of this function here. Now it has some kind of loss in comparison to Burns and Gong and Cervoli's natural result concerning non-volume preserving change of coordinates. But if we force this, then we get a power series of the sum of squares. Now, using Weil results, this author here, Saulowski, he's Polish, he has shown the following. If you take the germ function, which is right equivalent to the product of coordinates around the origin, then you also find a volume preserving change of coordinates in which this function f may be written as a power series of the product of coordinates, also uniquely determined up to sign, plus or minus. So we use this to show this result here. If M is a germ of irreducible singular real analytic Levi-flat hypersurface around the origin of Cn, such that it is the real part of this product of coordinates plus higher order real analytic terms, then if we assume that the singular set of the complexification of the Levi-flat is also the intersection of these hyperplanes, then we may find a new set of coordinates. Oh no, I'm sorry. We may find a foliation tangent to M with a non-constant holomorphic first integral of this form. Product of coordinates plus higher order holomorphic terms. such that m is simply the real part of this function. So recall that m was real part of something plus higher order terms in which you had no control over. And what is the most interesting thing in this theorem is that the dimension of the singular set of MC is higher than 0. Yeah, it's a very large singular set, for which we may also get a normal form, a volume preserving one, actually. This one. Simply a power series of the product of coordinates. Yeah, and the singular set of this is enormous. And in dimension 2, theorem 2 and this last corollary here are equivalent, right? Because the product of Z1 and Z2 and the sum of squares may be obtained from one another. This is not hard to show. Yeah, singular set is large enough. So, I guess that's it. This one.